There is one place in the solar system, other than this one, where you could stand outside without a pressure suit and be neither crushed nor boiled. The temperature is mild. The pressure is close to sea level. You would want an oxygen mask, and nothing more exotic than that. It is 50 kilometers above the surface of Venus, floating over a landscape hot enough to melt lead. Tonight we walk the whole solar system, world by world, asking the same quiet question at each one. How long would a person last standing here? The answers run from an instant to an afternoon, and every planet has its own particular way of saying no. If you would rather listen with the screen off, this channel is on Spotify too, and the link is in the description. Tell me in the comments where you are listening from and what time it is where you are. Now slowly, let your shoulders drop. There is nowhere to be for the next couple of hours. I want to say something about the shape of tonight before we set off, because a video about how quickly various worlds would kill you could easily be a tense thing, and this is not going to be. We are going to travel outward from the sun, and at each world we are going to stop and stand there for a while and consider what would happen. And what emerges, I think, is not horror. It is something closer to tenderness, because the answer at every single stop is no. Every one. 15 or so worlds, each with a completely different reason, each one arrived at by a completely different 4.5 billion year history, and every one of them, in its own particular way, gently declining. And there is exactly one place where the answer is yes, and you are lying in it. That is what this is really about, not danger, the other way around. So we will take our time. If you fall asleep somewhere around Jupiter, that is entirely fine, and the outer planets will still be there tomorrow, being extremely cold, quite patiently. Let's start with something in the room. You are, at this moment, being kept alive by 4 things you cannot see and have never once thought about. The first is pressure. There is a column of air above you, reaching up about 100 kilometers, and its weight presses on every part of you at about 1 kilogram per square centimeter. That pressure is what keeps the water in your blood and your tissues liquid rather than vapor. It is not optional, and it is not adjustable. The second is composition. Roughly 21% of the air moving in and out of you right now is oxygen, not more, which would make the world flammable in ways you would not enjoy, not less, which would put you to sleep permanently. And the other 78% nitrogen is doing something too. It is providing bulk, inert filler that keeps the pressure up without adding chemistry. The third is temperature. Your body runs a chemical process that only works within a very narrow band, and it holds itself at 37 degrees Celsius with impressive stubbornness. Push your core temperature 5 degrees either way, and the chemistry begins to fail. And the fourth is shielding. Above you, invisible, are the atmosphere and the magnetic field, and between them they are stopping the vast majority of the charged particles arriving from the sun and from the wider galaxy. 4 things: pressure, oxygen, temperature, shielding. You've never had to think about any of them, ever, not once in your life. And neither did anyone in your family going back to the beginning of the species. They are the 4 things that no other world in this solar system provides. So here is how we are going to do the arithmetic tonight, because how long you survive somewhere is really a question about which of those 4 runs out first. Think of them as 4 clocks, all running at once, and whichever reaches 0 soonest is the one that decides. The oxygen clock is the most familiar. stop breathing, and you have somewhere between 1 and 3 minutes before you lose consciousness, depending on how calm you are, and a few minutes beyond that before the damage becomes permanent. Free divers can stretch it considerably with training, but for an ordinary person startled and afraid, the useful number is short. The pressure clock is much faster and much less familiar, and we will spend some proper time on it in a moment because almost everything people believe about it is wrong. The temperature clock varies enormously. In extreme cold, with no protection, you have minutes to hours. In extreme heat, seconds to minutes. But there is a subtlety here that matters more than any other single fact in tonight's journey, and it is this. Temperature and heat are not the same thing. A number on a thermometer tells you very little on its own. What matters is how fast energy can actually move between you and your surroundings, and that depends almost entirely on what the surroundings are made of. Hold that thought. It is going to save us from a great deal of nonsense when we get to Mercury, and the radiation clock is the slow one. Nothing about radiation kills you in seconds at any dose you will encounter standing on a planetary surface. It kills you in hours, days, weeks, or decades, depending. Which makes it the clock that only matters on worlds where the other three have somehow been solved. All right, before we leave Earth, we need to be precise about what happens to an unprotected human body in a vacuum, because it comes up again and again tonight, and because the popular picture is almost entirely fiction. You've seen the film version. A person is exposed to space, and they swell up grotesquely and burst, or they freeze solid in an instant and shatter, or their eyes explode. None of that happens. Here is what actually happens, and we know it in some detail, because there have been accidents. And remarkably, people have survived them. The first thing to understand is that your skin is strong. It is an elastic containment vessel, and it is entirely capable of holding your insides in against 1 atmosphere of pressure difference. That is not a large pressure. A car tire holds 2 or 3 times that. You do not burst. What does happen is ebullition. Water at low pressure boils at low temperature, and we talked about the Armstrong limit in another episode. At about 63 millibars, water boils at body temperature. So the water in your exposed tissues, in your saliva, on the surface of your eyes, and the moisture lining your airways begins to turn to vapor. Not violently. It bubbles. Gas comes out of solution in your soft tissues, and they swell noticeably over seconds. The swelling is uncomfortable, and it is limited by the skin, and it is reversible if pressure is restored quickly. The second thing is that you have some time, not much, but a real countable amount, roughly 10 to 15 seconds of useful consciousness. That number is not about how fast the oxygen leaves your lungs. It is about how long it takes the blood already in your arteries to complete the trip from your lungs to your brain. There is a full circuit's worth of oxygenated blood in transit, and your brain gets to use it before the news arrives. After that, you lose consciousness, and after roughly 90 seconds to 2 minutes, the damage is likely to be beyond recovery. The third thing, and this is the one that surprises people most, is that you do not freeze quickly. Space is cold in the sense that there is nothing in it, but heat only leaves a body by 3 routes. Conduction, which requires contact with something. Convection, which requires a fluid to carry the heat away. And radiation, which works in a vacuum but is slow. In a vacuum, the first 2 are simply unavailable. There is nothing touching you and nothing flowing past you. You lose heat only by radiating it, and a human body radiates heat at a fairly leisurely rate, you would in fact be more likely to overheat in sunlight than to freeze in shadow over the short term. The most immediate danger and the one that determines the standard instruction is your lungs. If you hold your breath, the air inside them at 1 atmosphere has nowhere to go against a vacuum outside, and lung tissue is delicate. So the instruction drilled into anyone who works around vacuum chambers is to exhale. Empty your lungs and let them collapse. Now, the 2 accidents. On the 16th of August 1960, a United States Air Force captain named Joseph Kittinger rode a helium balloon to an altitude of 31,300 meters, which is about 102,000 feet over New Mexico. He was testing high-altitude escape systems, and he intended to jump. At that altitude, the pressure is around 10 millibars, well above the Armstrong limit, in the region where the atmosphere is not thin so much as essentially absent. During the ascent, the seal on his right glove failed, and the glove did not pressurize. He noticed his hand beginning to hurt and then to swell. He could see it. It eventually reached roughly twice its normal size, and he lost the use of it entirely. And he did not tell anyone. He judged, correctly as it turned out, that if he reported it, the mission would be aborted, and he had spent years preparing. He rode the balloon to altitude with one hand ballooning inside a failed glove, stepped off the gondola, fell for 4.5 minutes, and landed. His hand returned to normal within about 3 hours of reaching the ground. There was no permanent damage. The second accident is more extreme, and it is the reason we know as much as we do. In December of 1966, at the Manned Spacecraft Center in Houston, a technician named Jim LeBlanc was inside a vacuum chamber testing a prototype spacesuit under conditions simulating an altitude of around 36 kilometers, essentially vacuum. A hose disconnected. The suit lost pressure in about 10 seconds. LeBlanc later described the last thing he was aware of, and it is one of the strangest sentences anyone has ever spoken about their own body. He felt the saliva on his tongue begin to bubble and boil just before he blacked out. He lost consciousness after roughly 14 seconds. The technicians began emergency repressurization immediately, and a colleague went into the chamber before it had fully equalized in order to reach him. He regained consciousness at the equivalent of about 4,500 meters altitude, having been unconscious for well under a minute. He suffered an earache. That was all. He went back to work. So the honest summary of vacuum exposure is this: it is lethal quickly, and it is survivable if reversed within about 30 seconds, and it is not the explosive spectacle we have been shown. 15 seconds of consciousness, about 90 seconds to the point of no return. That is our baseline. Keep it in mind, because on several of tonight's worlds, vacuum is what actually does it, and everything else is scenery, right? Let's begin where the solar system begins, closest in, and work our way out into the dark. Mercury. It is a small world, 4,879 kilometers across, which makes it smaller than 2 of the moons we will visit later tonight. It is barely a third, larger than our own moon, and from a distance it looks remarkably like it, gray and cratered and quiet. It has almost no atmosphere. There is technically something there, a whisper called an exosphere, made of atoms knocked off the surface by the solar wind and by micrometeorites, so thin that the atoms essentially never collide with one another. The surface pressure is around 1,000th of a trillionth of Earth's. For our purposes, that is a vacuum, and it is close to the sun. Its orbit is quite elliptical, so the distance varies between about 46 and 70 million kilometers, which means the sun in Mercury's sky is between about 2 and 3 times the width it appears from here and delivers somewhere between 6 and 11 times the energy. The day side reaches about 430 degrees Celsius, hot enough to melt lead, tin, and zinc. The night side falls to about minus 180. And here is the thing that makes Mercury genuinely strange rather than simply hot. It rotates in a peculiar way. Mercury turns exactly 3 times on its axis for every 2 orbits around the Sun, a relationship called a 3-to-2 spin orbit resonance, and the arithmetic of that produces something remarkable. A year on Mercury is 88 Earth days. A single solar day on Mercury, from one sunrise to the next, is 176 Earth days, which means the day is 2 years long. Sunrise then 88 Earth days of continuous daylight, then 88 Earth days of continuous night. And because the orbit is so elliptical, Mercury speeds up near the Sun and slows down further out. And at certain longitudes, the Sun's motion across the sky actually reverses. It rises, climbs, slows, stops, moves backward for a few Earth days, stops again, and then resumes its journey west. From some places you would watch the sun rise, set again briefly, and then rise a second time. So, you are standing on the day side without a suit. Now the obvious answer is that you are instantly incinerated. 430 degrees, cremation temperature. That is not what happens, and understanding why is genuinely useful because it recurs throughout tonight. Temperature is not heat. Temperature tells you how energetic the particles in something are. Heat is the actual transfer of energy, and transfer requires a mechanism. On Earth, when you step into a hot room, energy reaches you by convection. Billions of air molecules strike your skin every instant, each one giving up a little energy. That process is extremely efficient because the air is dense. On Mercury, there is no air. There is nothing to carry heat to you. The regolith under your boots is at 430 degrees, and it will conduct heat into anything touching it, so your feet would be in serious trouble immediately. And the sun overhead is pouring radiant energy onto you at 7 or 8 times the intensity you would feel at a beach here, which would burn exposed skin quickly and painfully. But your body as a whole does not come up to 430 degrees. There is no mechanism to bring it there fast. What kills you on Mercury is not the heat. It is the vacuum, and it kills you on exactly the schedule we established a few minutes ago. 15 seconds of consciousness, 90 seconds to the point of no return. You would spend those 15 seconds in extraordinary pain with your feet burning and your skin blistering under a sun that fills a noticeable patch of the sky, and the pain would not be what ended it. The absence of pressure would. Step around to the night side and everything reverses. Minus 180 degrees. Still a vacuum. Still 15 seconds of consciousness. And this time you would not freeze either, for the same reason in the opposite direction. With no air to conduct heat away from you and nothing but the ground to touch, you would radiate heat slowly. Your body would still be warm when it stopped. Mercury's answer, day or night, in the sunlight or in the dark, is about 90 seconds, which is, and I want to note this because it is going to turn out to be significant, one of the more generous answers we will hear tonight. There is one more thing about Mercury worth knowing, and it is lovely. Those permanently shadowed craters near the poles, the ones the sun never reaches because Mercury's axis is almost perfectly upright, sit at temperatures below minus 170 degrees, permanently, forever, and they contain water ice. The Messenger spacecraft, which orbited Mercury from 2011 until it ran out of fuel and impacted the surface in April of 2015, confirmed it with radar bright deposits and neutron measurements, and eventually direct images of the crater floors. The closest planet to the Sun has ice on it, billions of tons of it sitting in the dark in craters that have not seen daylight since the solar system was young. Now let's go outward one step to the world that breaks every intuition, Venus. If you were told nothing else about the solar system and asked to guess which planet is hottest, you would say Mercury. It is closest. It is obviously the answer. It is not the answer. Venus is roughly twice as far from the Sun as Mercury, and the surface of Venus is hotter everywhere, all the time, including at night and at the poles. The mean surface temperature is 462 degrees Celsius. That is not a peak. That is the average, and Venus barely varies. Day and night, equator and pole, the temperature is essentially the same everywhere on the planet, within a few degrees. The atmosphere is so massive and so effective at moving heat around that it simply irons out every difference. And the atmosphere is the whole story. It is 96.5% carbon dioxide, with most of the rest nitrogen, and it is enormously thick. The surface pressure is about 92 times Earth's, 92 bar. To feel that here, you would need to descend about 900 meters into the ocean, which means the air at the surface of Venus is not really behaving like air at all. At 92 bar and 460 degrees, carbon dioxide is a supercritical fluid, a state that is neither gas nor liquid but something in between, with a density around 65 times that of the air in your room. It is more like a thin, hot, syrupy sea than an atmosphere. Winds at the Venusian surface are slow, a few kilometers an hour, but in a fluid that dense, a slow wind pushes like a current in water. Above all that, between about 45 and 70 kilometers up, is a permanent global cloud deck. It is not water, it is sulfuric acid in droplets, wrapped completely around the planet, which is why Venus is the brightest object in our sky after the sun and moon. It reflects about 3/4 of the light that hits it, and Venus turns backwards. Almost every body in the solar system rotates in the same direction it orbits, a leftover of the spinning disk everything formed from. Venus rotates the other way extremely slowly, taking 243 Earth days to turn once, which is longer than its year of 225 days. Nobody knows for certain why. A giant impact early on is the usual suggestion, or a slow tidal capture involving the atmosphere itself. So, you are standing on the surface of Venus without protection. This is the fastest no in the solar system. The heat arrives instantly because, unlike Mercury, there is a dense fluid touching every square centimeter of you, and it transfers energy with brutal efficiency. This is the difference between reaching into a hot oven, which you can do, and reaching into a pot of boiling water, which you cannot. Same principle, vastly more severe. Simultaneously 92 atmospheres of pressure. You could not draw a breath. The pressure differential would prevent your diaphragm from expanding your chest at all, and the first thing you inhaled would be 460-degree supercritical carbon dioxide, which would destroy the tissue of your airways immediately. Consciousness would last, at the outside, a second or two, almost certainly less, not minutes, not the 90 seconds Mercury gives you. A moment. We know how hostile it is because we have sent things there and watched them die. The Soviet Venera program is one of the most extraordinary and least celebrated engineering achievements of the 20th century. Between the 1960s and 1980s, the Soviet Union sent lander after lander to Venus, and the early ones were crushed on the way down because nobody had realized how thick the atmosphere was. They built them stronger. They built them stronger again. On the 15th of December, 1970, Venera 7 became the first spacecraft to transmit data from the surface of another planet. It landed hard, tipped over, and transmitted a weak signal for 23 minutes before falling silent. The signal was so faint that it was only recovered from the tapes weeks later on careful reanalysis. The program kept improving. Venera 9 in 1975 sent back the first photograph ever taken from the surface of another planet, a gray image of flat, broken rocks receding to a horizon. The high point came on the 1st of March, 1982. Venera 13 landed in a region called Phoebe Regio, and it was designed to survive 32 minutes. It lasted 127. In those 2 hours, it returned the first color images from the Venusian surface, showing flat orange-brown slabs of rock under a hazy orange sky, with part of the lander's own baseplate in frame and a lens cap lying on the ground where it had fallen. It drilled into the surface and analyzed the rock, and it recorded sound, actual audio from the surface of Venus, of wind moving through the thick air, and of the lander's own drill working. Then the heat got into the electronics and it stopped, as everything there always does. No lander has touched the surface of Venus since Vega 2 in 1985. 2 new missions, one American and one European, are being prepared, and the American probe is designed to fall through the atmosphere and sample it on the way down rather than to survive at the bottom. Because at the bottom, nothing survives for long. 2 hours has stood as the record for over 40 years, and now the exception. The one genuinely surprising thing in the whole solar system. Go up. Climb from that crushing, supercritical surface, up through the dense lower atmosphere, up past the base of the acid clouds, and at an altitude of around 50 to 55 kilometers, something remarkable happens. The pressure falls to about 1 bar. That is sea level. That is exactly what you are sitting in right now. And the temperature there, depending on precisely where you stop, sits somewhere between about 0 and 50 degrees Celsius. A warm afternoon. So at that altitude, floating in the cloud tops of the most hostile surface in the solar system, the pressure is Earth-like and the temperature is Earth-like. And the only reasons you could not simply breathe are that the air is carbon dioxide and there is sulfuric acid in the droplets around you. You would need an oxygen supply and protection from the acid. You would not need a pressure suit. You would not need heating or cooling. If your airline failed, you would have a couple of minutes rather than 15 seconds, because the pressure holding you together would still be there. Those are, by a wide margin, the most Earth-like conditions found anywhere off Earth. And there is a further quirk that makes it stranger. Because the Venusian atmosphere is mostly carbon dioxide, which is heavier than the nitrogen and oxygen mix we breathe, ordinary breathable air is a lifting gas on Venus. A balloon filled with the air in your room would float there, the way a helium balloon floats here, and it would have roughly half the lifting power that helium has on Earth. Which means a habitat on Venus does not need a separate envelope of lifting gas. The breathable volume is the balloon. A large sphere filled with ordinary air would float naturally at around 50 kilometers, and people could live inside it at sea level pressure and shirt sleeve temperature. This has been studied seriously. NASA's Langley Research Center developed a concept along these lines called havoc, and the physics is entirely sound. There is even a gravity advantage. Venus is almost the same size as Earth, and its surface gravity is 90% of ours, which means all the bone and muscle problems that make long stays on Mars and the Moon so difficult would largely not arise. The hottest, most crushing, most poisonous surface in the solar system, with the most comfortable spot in the solar system floating 50 kilometers above it. Nothing about this place makes sense until you look closely, and then it makes a great deal of sense, and it is still hard to believe. Which brings us home briefly, because Earth deserves a stop on this tour, and not for the obvious reason. The answer for Earth is a lifetime, 70 or 80 years, more if you are fortunate. That is the whole point of the exercise, but I want to complicate it slightly, because it is easy to picture Earth as uniformly hospitable, and it is nothing of the sort. Stand on the summit of Mount Everest, 8,849 meters up, and the pressure is around a third of sea level. The oxygen fraction of the air is unchanged at 21%, but the air itself is so thin that each breath delivers a third of what your body needs. Climbers call the region above 8,000 meters the death zone, and the name is literal. The body cannot acclimatize there. It is not adapting slowly, it is dying slowly. Digestion largely stops. Cognition deteriorates. Without supplementary oxygen, most people have hours to a day or so before judgment fails badly enough to be fatal. That is a place on this planet where the ceiling is a matter of hours, and people walk there. Go down instead. The deepest point of the ocean in the Mariana Trench is nearly 11 kilometers below the surface, and the pressure there is over 1,000 times sea level, more than 10 times the pressure at the surface of Venus. An unprotected human at that depth would not last a heartbeat. Walk to the interior of Antarctica in winter, and the air can reach below minus 80 degrees. Unprotected, that is minutes. So even here, the habitable band is thin. It is a shell a few kilometers thick, wrapped around a rock, and it is thinner than the skin on an apple proportionally. Most of Earth by volume would kill you promptly. We simply happen to live in the part that does not. Now let's go outward properly, and the next stop is somewhere 12 people have actually stood. The Moon. It is not a planet, and we are going to break the rules a few times tonight to include moons, because some of the moons are more interesting than some of the planets, and one of them is the friendliest surface we know of anywhere. The Moon has no atmosphere. There is an exosphere, as on Mercury, so thin that if you gathered up the entire gaseous envelope of the Moon, it would weigh about as much as a small office building. The temperature at the equator reaches about 127 degrees Celsius in daylight and falls to about minus 173 at night. And the day is long. A lunar day, sunrise to sunrise, is about 29.5 Earth days, which means roughly 14 days of unbroken sunlight followed by roughly 14 days of unbroken darkness. That is the single hardest engineering problem for a lunar base. Solar power works beautifully for 2 weeks and then stops for 2 weeks. And during those 2 weeks, the temperature drops by 300 degrees. In the permanently shadowed craters at the lunar South Pole, the temperature has been measured below minus 240 degrees Celsius, which makes them among the coldest places ever measured anywhere in the solar system, colder than the surface of Pluto. Those craters also contain water ice, which is why every space agency on Earth is currently interested in the lunar South Pole and not the equator. Your survival time, unprotected, is 90 seconds. The same number as Mercury. It is a vacuum, and vacuum is vacuum. But the Moon has a distinction. None of the other worlds tonight can claim, and it is worth pausing on. People have actually stood there. 12 of them between July of 1969 and December of 1972. 12 human beings have put their boots on the surface of another world and walked around, and every one of them came back. The longest anyone stayed was during Apollo 17, the last mission, when Eugene Cernan and Harrison Schmitt spent about 75 hours on the surface and around 22 of those hours outside the module. Schmitt was a professional geologist, the only trained scientist to make the trip, and he spent those hours doing field geology on the moon, which remains one of the most extraordinary sentences in the history of science. They also discovered the dust problem, which nobody had properly anticipated. Lunar regolith is not weathered by wind or water, so its particles are jagged, and it holds an electrostatic charge, so it clings to everything. It worked into the suit joints and abraded the seals. It came into the module on their clothing, and when they removed their helmets, they could smell it. A sharp, dry, burnt smell that Cernan compared to spent gunpowder. Schmitt developed a genuine allergic reaction with congestion and streaming eyes. Small detail, enormous implications for anyone planning to stay. And there is one more number that matters. The moon has no atmosphere and no magnetic field, so the radiation environment is roughly what you get in deep space, somewhere in the region of 1 to 2 millisieverts a day on the surface, several hundred times what you receive at home, and no shelter at all from a solar particle event. Apollo, in retrospect, was extraordinarily lucky. In August of 1972, between the Apollo 16 and Apollo 17 missions, a solar storm occurred that would have delivered a dangerous and possibly lethal dose to anyone caught on the surface in a suit. Nobody was there. The window between missions happened to be open. Outward again. Mars. We have spent a whole night on Mars in another episode, so tonight we will keep it brief and focus only on the clocks. The atmosphere averages around 6 millibars, which is roughly 0.6% of Earth's. It is 95% carbon dioxide, with oxygen at about 0.1%. The average surface temperature is around minus 63 degrees Celsius, with summer afternoons at the equator occasionally rising above freezing and nights falling far below. 6 millibars is well below the Armstrong limit, which means that on the surface of Mars, unprotected, the water in your body would begin to vaporize at your own body temperature, exactly as in a vacuum. So the answer is 90 seconds again. The thin air makes essentially no difference to the outcome. You would freeze marginally faster than on the moon, because there is a little gas to carry heat away, and that is the whole of the difference. But Mars is the first world tonight where the answer changes dramatically if you add equipment. On Mercury, on the moon, in the clouds of Venus, a suit buys you time. On Mars, a suit buys you a working day. An extravehicular suit of the kind used on the space station carries around 8 hours of consumables. On Mars, with the gravity at 38%, walking is easier and the metabolic load is lower. You could plausibly spend the whole of a Martian day outside, come back in, refill, and do it again the next day. That is a completely different category of answer. Everywhere else tonight, protection is a barrier holding back something that wants to kill you immediately. On Mars, protection is more like a coat, which is precisely why Mars is the one everybody talks about, and it is a fair reason. It is the only surface in the solar system where a person in a suit could work a shift. The limits there are the slow ones, radiation at around 0.67 millisieverts a day, perchlorate in the dust, 38% gravity working on the skeleton over years. Those are the clocks that matter on Mars, and they run in months and decades rather than seconds. Mars has 2 moons, and they are strange enough to be worth a stop. Phobos and Deimos were found in 1877 by Asaph Hall at the United States Naval Observatory in Washington during the same close approach of Mars that had Schiaparelli in Milan drawing his canals. Hall had almost given up, and his wife Angeline talked him into one more night. They are tiny. Phobos is about 22 kilometers across at its widest, and Deimos only about 12, and neither is round. They are lumpy and cratered and look like potatoes. Nobody is certain what they are. They may be captured asteroids, or they may be debris from a giant impact that reaccreted, and the evidence is genuinely ambiguous. Phobos orbits astonishingly close, only about 6,000 kilometers above the Martian surface. Our moon is 60 times further from us than that, and it goes around in 7 hours and 39 minutes, which is faster than Mars rotates. That has an odd consequence. From the Martian surface, Phobos rises in the west and sets in the east, and it does so twice in a single Martian day, because it is overtaking the ground beneath it. It is also falling. Tidal forces are drawing Phobos inward by a couple of centimeters a year, and in somewhere between 30 and 50 million years. It will either strike Mars, or more likely, be pulled apart by tidal stress and spread into a ring. Mars is going to have a ring. Not now, but it is coming. And the gravity on these 2 objects is so slight that the numbers stop feeling real. The escape velocity from Phobos is about 11 meters per second, which is roughly 40 kilometers an hour. That is within the range of a hard overarm throw. Standing on Phobos, you could throw a stone off the moon entirely and watch it go into orbit around Mars. On Deimos, it is about 5.5 meters per second, 20 kilometers an hour. A person can jump upward at around 4 meters per second on Earth. In a suit, hampered and clumsy, probably less, but it is close. Standing on Deimos, a healthy person in a good crouch would be at genuine risk of jumping themselves into space, slowly, permanently, with nothing to grab. Survival time on either, 90 seconds. But they may turn out to be the most useful real estate in the Martian system, because landing on and launching from something with almost no gravity costs almost no fuel. Before we leave the inner solar system, there is a region we have walked straight past, and it deserves a stop, because almost everything most people believe about it is wrong. Between the orbit of Mars and the orbit of Jupiter lies the asteroid belt. The picture in your head is probably from a film. Tumbling rocks packed close together, a pilot weaving frantically between them, collisions imminent. The reality is close to the exact opposite. The asteroid belt is one of the emptiest places you could possibly go. There are certainly a great many objects in it. Over 1 million larger than a kilometer across have been cataloged, and there are vastly more small ones. But the volume of space they are spread through is staggering. The average distance between any 2 sizable asteroids is on the order of 1 million kilometers, which is nearly 3 times the distance from here to the moon. If you were standing on an asteroid, in most cases you would not be able to see another one at all, except as a faint point of light indistinguishable from a star. 5 spacecraft have crossed the belt without any special shielding, and none of them noticed. The engineering concern was essentially zero, and the whole belt is small. If you gathered every asteroid together into one body, the total mass would be around 4% of the mass of our moon. It is not the wreckage of a destroyed planet, which was the old theory. It is material that never managed to become a planet because Jupiter's gravity kept stirring it up and preventing it from accumulating. About a third of that entire mass is in one object. Ceres is 940 kilometers across, and it is classified as a dwarf planet, the only one in the inner solar system. The Dawn spacecraft orbited it from 2015 to 2018 and found a world that is roughly a quarter water, ice by mass, with a surface of clays and salts. And it found bright spots. Inside a crater called Ocator, there are patches so reflective that they showed up as glowing dots in the approach images and puzzled everyone for months. They turned out to be deposits of sodium carbonate, salt, left behind where briny water reached the surface from below and the water sublimated away, which means Ceres has or recently had liquid brine underground in the asteroid belt. Its gravity is about 3% of Earth's, which produces some genuinely strange arithmetic. A person who can jump half a meter here could jump around 15 meters there and would be in the air for the better part of half a minute. You could not jump off, though. Escape velocity is around 500 meters a second, which is far beyond anything a human body can produce. The other large body is Vesta, 525 kilometers across, and it is a different kind of object entirely. Vesta is differentiated, meaning it melted early in its history and separated into a metallic core and a rocky mantle and crust, like a proper planet. It is essentially a protoplanet that never grew up. At its south pole, there is an impact basin 500 kilometers wide, nearly as wide as Vesta itself, and in the middle of that basin, the rebound peak rises about 22 kilometers, which puts it among the tallest mountains in the solar system. That impact threw an enormous quantity of material into space, and some of it eventually reached us. Roughly 1 in 20 of all meteorites found on Earth are pieces of Vesta. There are fragments of that specific asteroid sitting in museum drawers all over this planet, and we know exactly which world they came from. Survival time on either 90 seconds. It is a vacuum, like nearly everywhere. And since we have now said 90 seconds a great many times, let me talk for a moment about what it actually takes to change that number, because we've been treating a spacesuit as though it were an item of clothing, and it is nothing of the kind. A spacesuit is a spacecraft shaped like a person. The suit used for spacewalks from the space station weighs something in the region of 145 kilograms on Earth, which is more than most of the people who wear it. It takes hours to put on with assistance. It has around 14 layers, each doing a different job. A bladder to hold pressure, a restraint layer to stop the bladder ballooning, insulation against a temperature swing of nearly 300 degrees, and an outer shell tough enough to resist micrometeorites and abrasion. And it has a problem at its heart that turns out to be surprisingly hard. You would think you would pressurize the suit to 1 atmosphere, the same as the air in a spacecraft, and be comfortable. You cannot, because of what pressure does to a flexible container. Inflate a rubber glove to 1 atmosphere against a vacuum, and it becomes rigid, not stiff. Rigid. You could not close your fingers. Every single movement would mean fighting the internal pressure trying to push the joint straight, and the force required would exhaust anyone in minutes. So the suit runs at a much lower pressure, around 1/3 of an atmosphere, filled with pure oxygen so that the partial pressure of oxygen is still sufficient, which creates a new problem. Going from a cabin at normal pressure to a suit at 1/3 of that is exactly like a diver ascending too quickly. Nitrogen dissolved in the blood, comes out of solution as bubbles, and that is decompression sickness. The bends, and it is serious. The solution is a protocol, and it is tedious. Before a spacewalk, an astronaut spends hours breathing pure oxygen to flush nitrogen out of their tissues, sometimes combined with exercise and a period at reduced cabin pressure. Every spacewalk in history has been preceded by that quiet, boring, essential wait. Then there is heat. A suited person in sunlight is a sealed, insulated container with a warm animal inside it, and the animal is working hard. Getting rid of that heat is a bigger engineering problem than keeping warm. The answer is a garment worn against the skin, laced with something like 90 meters of fine tubing, through which cool water circulates continuously, carrying heat out to a device that dumps it by letting a small amount of water sublimate into space. And then there are the gloves, which are the hardest part of the entire suit and always have been. Every finger joint has to bend against the internal pressure, and doing that repeatedly for 6 or 7 hours causes real damage. Hand fatigue is the limiting factor on most spacewalks, and fingernail injuries are a documented and unpleasant occupational hazard. So when we say a suit turns 90 seconds into 8 hours, that is not a small adjustment. It is one of the most sophisticated pieces of engineering our species produces. It costs an enormous amount. It takes years to fit to an individual, and it is still uncomfortable enough that the people wearing it come back with damaged hands. That is the price of the 4 things you are getting for free right now. Onward. And now the character of the journey changes completely, because from here out there are no surfaces at all on the planets themselves. Jupiter. The first thing to understand is that the question we have been asking does not apply. There is nowhere to stand. Jupiter is a gas giant, and by that we do not mean a rocky world with a very thick atmosphere. We mean that as you descend, the hydrogen simply gets denser and hotter and more compressed, continuously, with no boundary anywhere. There is no point at which gas becomes liquid, because deep inside Jupiter, the temperature is above the critical point for hydrogen. And above that temperature, the distinction between gas and liquid stops existing. It is one substance grading smoothly into another state of itself. Far, far down, at perhaps 20,000 kilometers, the pressure becomes so extreme that hydrogen is squeezed into a state where its electrons come loose, and it conducts electricity like a metal. That metallic hydrogen ocean churning is what generates Jupiter's colossal magnetic field. There may be a rocky core beneath even that, or there may be something more diffuse. Juno's gravity measurements suggest the core is fuzzy rather than sharply defined. You would never reach any of it. Because Jupiter has no surface, scientists define a reference level at the pressure of 1 bar, the same as Earth's sea level, and use that as the 0 point for altitude. At that level, the temperature is about minus 107 degrees Celsius. Higher up, at the visible cloud tops, it falls to around minus 145. The gravity at the 1 bar level is about 2.5 times Earth's, which means falling is not a gentle experience. And it has weather of a kind that has no equivalent anywhere. The Great Red Spot is an anticyclonic storm sitting south of Jupiter's equator, and it has been observed more or less continuously since 1830. There are records of a similar feature going back to the 1660s, which may or may not be the same storm. There is a gap in the observations in the 18th century that nobody can bridge. If it is the same storm, it has been running for over 350 years. It is currently around 16,000 kilometers across, which is larger than Earth. It used to be considerably larger. Measurements from the late 19th century put it at perhaps 40,000 kilometers, and it has been shrinking steadily and getting rounder, and nobody knows whether that will stop. Winds at its edges run at something like 430 kilometers an hour, and the Juno spacecraft, using microwave instruments that can see below the cloud tops, found that the storm is not a shallow surface feature. It extends several hundred kilometers down into the atmosphere, far deeper than anyone expected, with roots below the level where sunlight can reach. Juno also photographed the poles, which no spacecraft had properly seen before, and found something nobody predicted. At the North Pole, 8 enormous cyclones, arranged in a regular octagon around a ninth at the center. At the South Pole, 5 arranged around one. Each of them is roughly the size of a continent, and they have held that geometric arrangement for as long as we have been watching. Nothing on Earth does that. Our storms form, move, and die within days. So what happens if you fall into Jupiter? You would enter the cloud tops in 100 degrees below freezing, in an atmosphere of hydrogen and helium with no oxygen whatsoever at 2.5 gravities. Suffocation and hypothermia would both be running fast. Consciousness would last seconds, and then you would keep falling for a very long time, and the temperature would begin to climb. You would pass through the ammonia clouds, then the ammonium hydrosulfide layer, then what is thought to be a deck of water clouds. The pressure would rise past 10 bar, past 100, past 1,000. Somewhere in there, whatever was left would be thoroughly destroyed, and the atoms would join the planet, and there would be no landing. Ever. Just a gradual merging into something denser. We know a certain amount about that descent because we have done it. On the 7th of December 1995, a probe released from the Galileo spacecraft 5 months earlier entered Jupiter's atmosphere at 47.8 kilometers per second. That is the fastest atmospheric entry ever attempted by anything human beings have built. In the first 2 minutes, it decelerated at up to 228 times Earth gravity, and the front of its heat shield reached around 16,000 degrees Celsius, more than twice the temperature of the surface of the sun. Roughly half the mass of the heat shield burned away in those 2 minutes. Then, subsonic at last, it deployed a parachute and began the descent it had been built for. It transmitted for about 58 minutes as it fell, measuring temperature, pressure, wind, composition, and lightning, and relaying everything up to the orbiter passing overhead. It reached a pressure of about 22 bar and a temperature of about 152 degrees Celsius, some 150 kilometers below its entry point. Then the heat silenced its transmitter. The probe kept falling. Analysis suggests the parachute would have melted around an hour and 3/4 after entry, and the aluminium structure some 40 minutes after that. There was no impact. Nothing struck anything. It simply became part of Jupiter. 58 minutes of data from a planet nearly 140,000 kilometers across, sampling the outermost skin of it. That is everything we have ever measured from inside a gas giant. And there is one more thing about Jupiter that decides the fate of everything near it, and it is invisible. Jupiter's magnetic field is the largest structure in the solar system apart from the sun's own influence. Its magnetotail stretches out toward the orbit of Saturn, and it traps charged particles, accelerating them to enormous energies, producing a radiation environment around 20,000 times more intense than Earth's Van Allen belts, which brings us to 4 of the most interesting places in the solar system, all of them sitting inside that: Io, Europa, Ganymede, and Callisto. Galileo Galilei saw them through a small telescope in January of 1610 and realized they were circling Jupiter rather than Earth, and that observation did more damage to the medieval picture of the cosmos than almost anything else. Take them in order, moving outward. Io is the innermost, and it is the most volcanically active body in the solar system by an enormous margin. It has somewhere around 400 active volcanoes. Plumes rise hundreds of kilometers above the surface. The whole moon is being kneaded by Jupiter's gravity and by the pull of the other moons, and the friction of that flexing keeps its interior molten. It looks in the images like something that has gone badly wrong, yellow and orange and white, mottled with sulfur compounds, with dark volcanic scars. The radiation there is the worst of the 4 by a wide margin. Estimates put the surface dose in the region of 36 sieverts a day. To calibrate that against something, the whole Mars mission we discussed in another episode, Out and Back, comes to about 1 sievert. Io delivers 36 times that in 24 hours. Standing on Io unprotected, you would die of vacuum in 90 seconds. But even in a perfect suit with air and warmth and pressure, you would be receiving a fatal radiation dose within a couple of hours, and you would be dead within days, no matter what happened afterwards. Europa is next, and it is the one that fascinates everybody because underneath its shell of ice, which is somewhere between 15 and 25 kilometers thick, there is a global ocean of liquid salt water, perhaps 60 to 150 kilometers deep. That ocean contains more liquid water than all the oceans of Earth combined. It has been there, kept liquid by tidal heating, probably for billions of years. It is in contact with a rocky seafloor, which means chemistry. It is, by a fair number of assessments, the most promising place in the solar system to look for life beyond Earth, and the surface above it is one of the most lethal places we know. The radiation dose at Europa's surface is about 5.4 sieverts per day. That is enough to cause severe radiation sickness or death from a single day's exposure. Recent mapping using Galileo and Voyager data has shown it is not uniform. The harshest zones are in oval regions around the equator, and the poles receive considerably less. Your 90 seconds of vacuum survival would be the least of it. In a suit, you would have hours before the dose became irrecoverable. Ganymede is next out, and it is the largest moon in the solar system. It is bigger than the planet Mercury. If it orbited the sun on its own, nobody would hesitate to call it a planet. And it has something no other moon has: its own magnetic field, generated by a liquid iron core sitting inside Jupiter's vastly larger one. It creates a small protected bubble, and the radiation dose there drops to something in the region of 1/15 of a sievert per day. Still far too much for a long stay, but a different order of problem. And then Callisto, the outermost of the 4 and the quiet one. Callisto orbits far enough out to sit largely beyond the worst of Jupiter's radiation belts. The dose there is roughly a 10,000th of a sievert a day, which is comparable to what an astronaut receives in low Earth orbit. It is heavily cratered, geologically dead, and almost certainly has a subsurface ocean of its own. A NASA study in the early 2000s examining human exploration of the outer solar system identified Callisto as the only body in the Jovian system where a crude base would be practical precisely because of that radiation shadow. So within one small family of 4 moons, all discovered on the same nights in 1610 by one man with a homemade telescope, you have the most volcanically violent object in the solar system, the most promising place to look for life, the largest moon anywhere, and the only realistic harbor for people. And on all 4 of them, the answer to tonight's question is the same 90 seconds, because all 4 are in vacuum. It is only when you put a suit on that they begin to differ, and then they differ enormously. Saturn. Everything true of Jupiter is true here, in a slightly gentler register. No surface. Hydrogen and helium grading downward into something denser without any boundary. A 1-bar reference level where the temperature is about minus 178 degrees Celsius. Saturn is less dense than water. If you had a bathtub large enough, Saturn would float in it, which is a fact that has appeared in every children's astronomy book for 80 years and is nonetheless true and slightly absurd. The winds are faster than Jupiter's. Around the equator, they reach something like 1,800 kilometers an hour, which is well over 4 times the strongest tornado ever recorded on Earth. And at the North Pole, there is a hexagon. This is one of the strangest things in the solar system, and nobody predicted it. A jet stream at Saturn's North Pole flows in a shape with 6 distinct straight sides and 6 corners, roughly 30,000 kilometers across, wider than 2 Earths. It was first seen by Voyager in 1981, and it was still there when Cassini arrived a quarter of a century later, and it is still there now. It appears to be a stable, standing wave in the jet stream, and something similar can be produced in laboratory experiments with rotating fluids, so it is not mysterious in the sense of being unexplained. It is simply astonishing that a planet has a geometric figure at its pole and keeps it there for decades. And then there are the rings, which are the most photographed structure in the solar system and are almost never described accurately. They span about 280,000 kilometers from the inner edge to the outer, which is nearly 3/4 of the distance from the Earth to the Moon. And they are, on average, about 10 meters thick. 10 meters. A structure wider than the Earth-Moon system and thinner than a 4-story building. If you scaled the rings down to the width of a football pitch, they would be thinner than a sheet of paper. There is nothing else in nature with that ratio. They are made almost entirely of water ice, over 99% pure, which is why they are so bright. The particles range from dust grains up to chunks the size of a house, with most of the mass in pieces from a centimeter to a few meters across, all of them orbiting independently, each on its own path, jostling and colliding gently and constantly. So there is no surface there either. You could not stand on the rings. You could float among them in vacuum, surrounded by tumbling boulders of clean ice at minus 180 degrees, with the nearest one perhaps a few meters away and perhaps a few hundred. 90 seconds again, unprotected. In a suit, it would be one of the more extraordinary places a person could ever be. And here is what Cassini found, which changed how we think about them. The rings appear to be young, estimates based on how quickly interplanetary dust should darken clean ice, and on measurements Cassini made of the total ring mass during its final orbits, suggest an age of perhaps 100 million to a few 100 million years, which means that when dinosaurs walked on Earth, Saturn may have had no rings at all, and they are going away. Cassini measured material falling out of the rings and into Saturn's atmosphere, a process nicknamed ring rain, and the rate is high enough that the whole structure may be gone within a few 100 million years. The rings are not an ancient permanent feature of the solar system. They are a temporary event, and we happen to be alive during it. Something, perhaps a moon that wandered too close and was torn apart by tides, was destroyed relatively recently, and the debris spread into a disk, and it is slowly draining away, and we arrived in time to look at it. The answer to tonight's question at Saturn is the same as at Jupiter. There is nowhere to stand, and if you were dropped into the cloud tops, you would have seconds, and then a very long fall, and no landing. Cassini itself ended that way, deliberately. On the 15th of September 2017, after 13 years in orbit, with its fuel nearly gone, the spacecraft was steered into Saturn's atmosphere rather than left adrift because there was a real possibility it might eventually strike Enceladus or Titan and contaminate them with terrestrial microbes. It transmitted until it broke apart. That was a decision made out of care for two places nobody has ever visited. And one of them is where we are going now, and it is the reason I wanted to do this episode. Titan. Christian Huygens found it in 1655. Using a telescope, he had ground the lenses for himself. It is the second largest moon in the solar system, 5,150 kilometers across, which makes it larger than the planet Mercury, and it is the only moon anywhere with a substantial atmosphere. Not a wisp, not an exosphere, a real thick blanketing atmosphere, so opaque and orange that for 300 years nobody could see the surface at all. Voyager flew past in 1980 and photographed a featureless amber ball. The surface pressure on Titan is 1.45 bar. Read that again, because after everything we have discussed tonight, it should stop you. 1.45 bar. That is 1.5 times the pressure you are sitting in. Titan has more air pressure at its surface than Earth does, and the composition is about 95% nitrogen, which is the same gas that makes up most of the air in your lungs right now, with most of the rest being methane. So on Titan, for the first and only time on this entire journey, you would not need a pressure suit. Sit with what that means. On every other world tonight, the fundamental problem is that the outside wants to pull you apart, and the only answer is to live inside a sealed vessel forever. On Titan, the outside is pressing on you slightly harder than home does. Your blood stays liquid. Your eyes stay wet. Your lungs work normally. You would need two things and only two. Oxygen, because there is none, and you would carry a mask and a tank exactly as a diver does. And insulation, because it is minus 179 degrees Celsius. That second one is serious. Cold that deep in a dense atmosphere that conducts heat away efficiently would kill an unprotected person quickly in minutes rather than the hours you might get in still, thin, cold air. Titan's atmosphere is good at stealing heat, but insulation is a solved problem. It is a coat, a very good coat with a heater in it, of the kind that already exists rather than a pressurized metal shell. The practical answer then is that on the surface of Titan, in a heated suit and an oxygen mask, a person could survive for as long as their tank and their batteries lasted. Hours, comfortably, with a rebreather and a decent power supply, potentially a great deal longer than that, and you would not be standing in a still dead place. Titan is the only world besides Earth with stable liquid on its surface, not water. At 94 Kelvin, water is rock. Methane and ethane, which at that temperature are liquids and which fall as rain. There are lakes, there are seas. In the northern hemisphere, Kraken Mare covers an area larger than the Caspian Sea. Ligeia Mare and Punga Mare sit near it. Radar mapping by Cassini shows shorelines, bays, islands, and river channels feeding down into them from the highlands. It rains on Titan. Rarely, in most places, but genuinely. Methane evaporates from the seas, forms clouds, and falls. There is a hydrological cycle with the wrong liquid, running at a temperature where the rocks are made of water ice. Near the equator, there are dune fields hundreds of kilometers across, made not of sand but of dark grains of complex organic material that forms in the upper atmosphere when sunlight breaks apart methane and the fragments recombine. That material drifts down and piles up into dunes shaped by the wind. And there is almost certainly a global ocean of liquid water beneath the ice crust, dozens of kilometers down. We have been there. Once. The Huygens probe, carried to Saturn by Cassini and released in December of 2004, entered Titan's atmosphere on the 14th of January 2005 and descended by parachute for 2.5 hours, photographing as it went. The images from the descent show, unmistakably, a landscape carved by flowing liquid, branching drainage channels running down from bright highlands to a darker plain. It landed with a soft thud on a surface that behaved rather like wet sand, and it kept transmitting from the ground for about 72 minutes, until Cassini passed below the horizon and the relay was lost. It had been designed to survive perhaps 3 minutes on the surface. The photograph it sent from the ground shows scattered rounded pebbles, 10 or 15 centimeters across, sitting on a flat orange-brown plain. They are rounded the way river stones are rounded, because that is what they are. Water ice cobbles, tumbled smooth by liquid methane. That is still the most distant landing human beings have ever achieved, and it happened once 20 years ago and lasted an hour and a quarter. And now the part that everyone remembers about Titan. Titan's gravity is about 14% of Earth's, which is a little less than the Moon's, and its atmosphere is roughly 4 times denser than ours at the surface. Low gravity, thick air. Put those two together and you get a result that sounds like fantasy and is simply arithmetic. A person on Titan wearing a pair of wings strapped to their arms could fly. Not glide. Fly under their own muscle power by flapping. The lift you generate depends on the density of the air you are pushing against and the area you are pushing with. The weight you must overcome depends on gravity. On Titan, the air gives you 4 times the purchase, and the gravity asks for 1/7 the effort, and the combination puts human-powered flight comfortably within reach of an ordinary person with modest equipment. You would need to be in a heated suit with an oxygen tank, and the suit would be bulky, and none of that changes the physics. Somewhere out there, 1.5 billion kilometers away, under an orange sky beside a sea of liquid methane, in the coldest weather imaginable, there is a place where a human being could put on a pair of wings and take off. NASA is going back. A mission called Dragonfly is being prepared, and it is not a lander or a rover. It is a rotorcraft, a nuclear-powered drone about the size of a small car, designed to fly between locations on Titan's surface, landing, sampling, and hopping onward. It is scheduled to arrive in the mid-2030s. Of everything we have talked about tonight, that is the one I find hardest to stop thinking about. A machine flying in the atmosphere of a moon of Saturn. There is one more world in the Saturn system worth stopping for, and it is small and bright, and it has geysers. Enceladus is only about 500 kilometers across. You could drive its circumference in a couple of days if there were roads. It is the most reflective body in the solar system, bouncing back around 80% of the light that falls on it, which is why its surface temperature is minus 201 degrees. It refuses to absorb the little sunlight it gets. And in 2005, Cassini noticed something odd about the magnetic field near it, and looked closer and found plumes. From 4 long fractures near the South Pole, informally called the Tiger Stripes, jets of water vapor and ice particles are erupting into space continuously. Some of the material falls back. Some of it escapes entirely and forms one of Saturn's outer rings. Cassini did something remarkable. It flew directly through the plumes more than once and sampled them. In that spray it found water, of course, salts indicating that the source is a salty ocean in contact with rock, silica nanoparticles of a kind that on Earth form in hydrothermal systems at temperatures above about 90 degrees Celsius, which implies hot water meeting rock on a seafloor, molecular hydrogen, which is a usable energy source for certain kinds of microbial life, and a range of organic molecules, some of them surprisingly large. A small icy moon in the outer solar system is spraying the contents of its subsurface ocean into space where a passing spacecraft can taste it. You would last 90 seconds standing there. It is a vacuum, like nearly everywhere else. But it may be one of the 2 or 3 most likely places in the solar system where something is alive, and it is telling us about itself continuously without being asked. Let me pause the tour for a moment because a pattern has been forming, and I want to name it before we go further out. Imagine a very long corridor with many doors, and behind each door a different room. You walk down it opening doors. Behind the first, the room has no air in it, and you have a minute and a half. Behind the second, the room is an oven full of hot syrup, and you have a second. Behind the third, no air again, 90 seconds. The fourth, the same. The fifth is not a room at all. The floor gives way, and you fall forever. Door after door after door. And every single one is a no, and the no's are all different, and none of them are personal. Nothing out there is hostile. Hostility requires intent. Venus is not trying to kill you. Venus is a rock with a great deal of carbon dioxide on it, arranged by 4.5 billion years of ordinary physics, and it happens that the arrangement is incompatible with the chemistry you are made of. The whole solar system is indifferent, and indifference is not cruelty. It is simply the default condition of matter. And then, at the far end of that corridor, there is one door, and behind it there is a room with air in it at the right pressure and the right temperature, and a magnetic field over the roof, and it has been like that for a very long time. And everyone you have ever loved is in there. The no's are what make the yes legible. If every door opened onto a garden, you would never notice you were standing in one. Now let's finish the corridor, because there are a few doors left, and they are the coldest. Uranus. It was the first planet ever discovered. Everything from Mercury to Saturn is visible to the naked eye, and has been known to every culture that ever looked up. Uranus was found by William Herschel from his garden in Bath, in England, on the 13th of March, 1781, and at first he thought it was a comet. It is an ice giant rather than a gas giant, which is a real distinction. Jupiter and Saturn are overwhelmingly hydrogen and helium. Uranus and Neptune have a great deal more of what planetary scientists loosely call ices, meaning water, ammonia, and methane, in a hot, dense fluid mantle. The methane in the upper atmosphere absorbs red light, which is why the planet is that particular pale blue-green. Two things about Uranus are genuinely peculiar. The first is that it is lying down. Its axis is tilted by about 98 degrees, which means it is not so much spinning like a top as rolling around its orbit like a ball. Most likely something very large struck it early on, and it never recovered. The consequence is the most extreme seasons anywhere. Uranus takes 84 Earth years to orbit the Sun, and for a substantial part of that, one pole is pointed almost directly at the Sun while the other is in complete darkness. A polar summer lasts about 42 years of continuous daylight, followed by 42 years of continuous night. The second peculiarity is the cold. At the 1 bar level, the temperature is about minus 197 degrees Celsius, but higher up, near the tropopause, it drops further, and the minimum recorded temperature in the atmosphere of Uranus is around minus 224 degrees. That is the coldest temperature ever measured in the atmosphere of any planet in the solar system. Colder than Neptune, which is half again as far from the Sun. Nobody is entirely sure why. Neptune has a substantial internal heat source, radiating considerably more energy than it receives from the Sun. Uranus appears to have almost none, which suggests that whatever event knocked it over may also have disrupted its ability to bring heat up from its interior. We have visited Uranus exactly once. Voyager 2 flew past in January of 1986, spent a few hours gathering data, and left. Everything we know about the surface conditions of that world comes from a single afternoon 40 years ago. Your survival there is the same as at the other giants. There is no surface, seconds of consciousness in the cloud tops, and then a fall into an ocean of hot, dense, electrically conducting water and ammonia that has no bottom you could reach. But Uranus has moons, and one of them is worth the detour. Miranda is small, about 470 kilometers across, and it looks like it was assembled by someone who had been given the pieces of several different moons and no instructions. Enormous grooved regions sit beside ancient cratered plains with sharp boundaries between them, as though slabs of different worlds had been fitted together. And on it stands Verona Rupes, a cliff face that drops something in the region of 20 kilometers. It is the tallest known cliff anywhere in the solar system, more than 10 times the depth of the Grand Canyon. Miranda's gravity is so low that if you stepped off the top of it, you would fall for around 12 minutes before reaching the bottom. 12 minutes of falling in a vacuum in near total silence, with the pale blue-green disk of Uranus somewhere above you. You would be dead long before you landed, of course, 90 seconds. But in a suit with the arithmetic done properly, that fall would be one of the most extraordinary experiences physically available in this solar system. Neptune, the last planet by most definitions and the only one discovered by mathematics before it was seen. In the 1840s, Uranus was not behaving. Its orbit did not match predictions, and the discrepancies were small but stubborn. Urbain Le Verrier in France and John Couch Adams in England independently worked backward from the deviations to calculate where an unseen planet would have to be to cause them. Le Verrier sent his prediction to the Berlin Observatory, and on the night of the 23rd of September 1846, Johann Galle pointed a telescope at the specified coordinates and found Neptune within an hour, within 1 degree of the predicted position. That is one of the great moments in the history of science, a planet located by pencil and paper. Neptune sits about 30 times further from the Sun than Earth. Sunlight there is about 1,000th of what falls on us, which means the Sun in Neptune's sky is a very bright star rather than a disk. Noon on Neptune is roughly as bright as deep twilight here. The temperature at the 1 bar level is about minus 201 degrees Celsius. And yet Neptune has the fastest winds ever measured anywhere in the solar system. Speeds around the equator reach something in the region of 2,100 kilometers an hour, which is faster than the speed of sound in Earth's atmosphere. That is a genuine puzzle. Weather is driven by energy, and Neptune receives almost none from the Sun. The answer appears to be that it has a substantial internal heat source, radiating over twice the energy it absorbs, left over from its formation and from ongoing gravitational settling. Voyager 2 passed Neptune in August of 1989 and photographed a large dark storm, comparable in scale to Jupiter's Great Red Spot, which was named the Great Dark Spot. When Hubble looked a few years later, it had gone. Others have appeared and vanished since. Neptune's storms are transient. In a way, Jupiter's are not. That flyby was the last thing Voyager 2 did in the planetary system. After Neptune, it turned outward, and it has been traveling ever since, and it is still transmitting. And Neptune has Triton, which is one of the strangest objects anywhere. Triton orbits backwards. It goes around Neptune in the opposite direction to the planet's rotation, which no large moon formed in place could do. It is almost certainly a captured object, a body from the Kuiper belt that wandered too close and was taken. Its surface temperature is around minus 235 degrees Celsius, which makes it one of the coldest surfaces ever measured in the solar system. And it is geologically active. Voyager photographed dark streaks on the pale surface and traced them back to plumes, jets of nitrogen gas, and dark particles rising 8 kilometers into the almost non-existent atmosphere and then being blown downwind. Something is powering geysers on a world at minus 235 degrees. Triton has a thin nitrogen atmosphere, about 100,000th of Earth's pressure, and a young, resurfaced landscape, and it is slowly spiraling inward. In a few billion years, Neptune's tides will tear it apart and give the planet a ring system to rival Saturn's. Your survival on Triton, unprotected, is 90 seconds. In a suit, it would be one of the more beautiful places to stand. Pale pink and white nitrogen frost underfoot, black plumes leaning downwind, and Neptune filling a large part of a sky the color of deep night, with the sun a bright point among the stars. Pluto. We should say something about the classification briefly and without arguing about it. Pluto was called the 9th planet from its discovery by Clyde Tombaugh in 1930 until 2006, when the International Astronomical Union adopted a definition requiring a planet to have cleared its orbital neighborhood, and Pluto has not. It shares its region with a great many other objects. It was reclassified as a dwarf planet. Whether that was a good decision is a matter people feel strongly about, and it does not change anything about the world itself. Pluto is about 2,370 kilometers across, smaller than our moon. Its orbit is elliptical and tilted, and it takes 248 years to go around once. The surface temperature is around minus 229 degrees Celsius. It has an atmosphere, and this is where it becomes interesting. A thin nitrogen atmosphere with some methane and carbon monoxide at a surface pressure of around 1 Pascal, which is about 100,000th of Earth's. And the atmosphere comes and goes. When Pluto is closer to the Sun in its orbit, surface ices sublimate and the atmosphere thickens. As it moves away, the atmosphere freezes out onto the surface as frost. Pluto has a breathing cycle 2.5 centuries long. For most of history, it was a dot. Even Hubble could resolve it only as a few blurry pixels. Then, on the 14th of July 2015, after a journey of 9.5 years, the New Horizons spacecraft flew past at 14 kilometers per second and turned a smudge into a world. What it found astonished everyone. Pluto was supposed to be a dead, cratered, frozen relic. Instead, there were mountains of water ice rising 3 kilometers high. There were hazes in the atmosphere, layered, extending 200 kilometers up. And there was Sputnik Planitia, an enormous heart-shaped plain of nitrogen ice, 1,000 kilometers across, almost entirely free of craters. No craters means young. A surface with no impact scars is a surface that has been renewed recently, geologically speaking. And close inspection showed the plain is divided into polygonal cells, tens of kilometers across, which appear to be convection cells. The nitrogen ice is slowly overturning, warm material rising in the middle of each cell and sinking at the edges, like the surface of a very slow, very cold pot of soup. Something is still going on inside Pluto, 4.5 billion years after it formed, 5.5 billion kilometers from the Sun. Standing there, unprotected, the answer is our familiar 90 seconds. 1 Pascal is not enough pressure to make any difference at all, but it would be an astonishing place to stand in a suit. Nitrogen ice underfoot, mountains of water ice on the horizon, a pale blue haze in the sky at sunset, and Charon overhead. Charon deserves its own mention. It is half Pluto's diameter, which is an enormous ratio. No other moon in the solar system is that large relative to its planet. The two are tidally locked to each other, both of them, which means Charon hangs permanently fixed in Pluto's sky, never rising and never setting, always at the same point, always showing the same face. From the other hemisphere of Pluto, you would never see it at all. And beyond Pluto, the Kuiper Belt continues, with Eris and Makemake and Haumea and Sedna and thousands of catalogued objects and probably billions more, out into a region where the sun is just the brightest star. And beyond even that, at distances of thousands to tens of thousands of times the Earth-Sun distance, there is thought to be the Oort cloud, a vast spherical shell of icy bodies loosely bound to the sun, so far out that passing stars can nudge objects loose from it. It has never been directly observed. It is inferred from where long-period comets come from, which is every direction at once rather than from the plane of the planets. Comets themselves are worth a moment because we have landed on one. A comet nucleus is a small body of ice, dust, and dark organic material. And one of the surprises of studying them closely is how dark they are. The nucleus of Halley's Comet reflects about 4% of the light that hits it, which is darker than charcoal. What we see when a comet is bright is not the nucleus. It is the coma and tail of gas and dust boiling off it as it nears the sun. In November of 2014, the European Space Agency's Rosetta mission released a small lander called Philae toward a comet named 67P Churyumov-Gerasimenko, a lumpy two-lobed object about 4 kilometers long. The escape velocity there is about 1 meter per second, walking pace. Philae's harpoons failed to fire, and it touched down and simply bounced. It rose off the surface and traveled for nearly 2 hours before coming down again, bounced a second time, and finally came to rest in a shadowed crevice where its solar panels could not get enough light. It worked for about 60 hours on battery power and returned data from the surface of a comet, which nobody had ever done before. The image of that is hard to shake. A machine landing so gently on something so small that it drifted away again and had to wait 2 hours to come back down. A person standing on 67P could not jump carefully enough to stay. Any ordinary movement would launch them off it. There is one thing out there past all of it that is ours. 2 spacecraft launched in 1977 within a fortnight of each other took a route made possible by an alignment of the outer planets that occurs roughly once every 176 years. Voyager 2 went to Jupiter, Saturn, Uranus, and Neptune, and remains the only spacecraft ever to have visited the last 2. Voyager 1 took a faster path past Jupiter and Saturn and then turned upward out of the plane of the planets. Both carry a gold-plated copper record with music and greetings in 55 languages and images of Earth encoded on it, along with instructions for playing it, aimed at nobody in particular. On the 14th of February, 1990, at Carl Sagan's suggestion and after years of persuasion, Voyager 1 was turned around to photograph the planets it had left behind. From 6 billion kilometers away, Earth occupied less than a single pixel caught in a shaft of scattered sunlight in the camera optics. That image is called the pale blue dot, and it is the most distant photograph of this planet ever taken. Voyager 1 crossed the heliopause, the boundary where the sun's wind gives way to the wind between the stars, in August of 2012. Voyager 2 followed in November of 2018. Both are now in interstellar space. Both are still transmitting faintly on a few watts of power using computers less capable than a modern washing machine. 49 years after launch. Survival time for a human at that distance would be 90 seconds, like almost everywhere. But there is nothing there to stand on and nothing to see except a sky full of stars, one of which is slightly brighter than the rest. There is one more place, and I've been saving it, and the answer there is the shortest of all. The sun. It is not a planet, and you cannot stand on it, and the arithmetic is barely worth doing. The visible surface is around 5,500 degrees Celsius, and above it the corona reaches 1 to 3 million degrees, for reasons that are still not fully understood and remain an active research problem. A human being approaching the sun would not have a survival time measured in seconds. It would be measured in the fraction of a second it takes for tissue to be converted into plasma at a distance of many hundreds of thousands of kilometers from anything you could call a surface. But we have sent something. The Parker Solar Probe, launched in 2018, has been flying progressively closer, with each orbit protected by a carbon composite heat shield, about 11 centimeters thick, that keeps the instruments behind it near room temperature, while its outer face reaches over 1,000 degrees. On Christmas Eve of 2024, it made its closest approach, passing about 6.1 million kilometers from the solar surface inside the corona itself, traveling at around 690,000 kilometers an hour. That is the fastest any human-made object has ever moved, and the closest anything of ours has ever come to a star. It survived, and it kept working, and it is still going. So let's gather it all up gently and look at the whole list at once. Here is the solar system, ranked by how long an unprotected human being would remain conscious and alive. At the very bottom, the sun. A fraction of a second at a distance where you would still be nowhere near it. Then Venus at the surface. 1 second, perhaps 2. crushed at 92 bar, cooked at 462 degrees by a fluid dense enough to transfer that heat instantly, unable to draw a single breath. Then the gas and ice giants, all four of them together. Jupiter, Saturn, Uranus, Neptune. A few seconds of consciousness in the cloud tops, from cold and suffocation, and at Jupiter, 2.5 gravities pulling you down, and then no ground ever. The fall is the whole answer. Then, grouped together at 90 seconds, almost everything else. Mercury, on the day side and on the night side alike. The Moon, Mars, Io, Europa, Ganymede, Callisto, Enceladus, Triton, Pluto, Miranda, Ceres. Every airless or nearly airless body we know of. 90 seconds. The same number over and over, on a dozen wildly different worlds. Because once the pressure is gone, the details stop mattering. It does not matter whether the ground is 400 degrees or minus 230. It does not matter whether there are volcanoes or oceans or nothing at all. Vacuum is vacuum, and the clock reads the same everywhere. That uniformity is one of the quiet surprises of doing this exercise. You expect variety, and what you actually find is one answer repeated across most of the solar system, with a handful of exceptions at either end. And then, at the top, the two exceptions. Titan, where the pressure is 1.5 times Earth's, and the only problems are oxygen and cold. Ours in a heated suit with a tank, and no pressure vessel needed at all. And the cloud tops of Venus, 50 kilometers above the worst place in the solar system, where the pressure is 1 bar and the temperature is shirt sleeve, and you would need a mask and acid protection and nothing else. Those two and Earth. That is the entire list. In a solar system containing 8 planets, 5 recognized dwarf planets, and something in the region of 300 moons, there are exactly 2 locations, besides this one, where the pressure and temperature are not immediately and totally lethal, and one of them is not on a surface at all. Now that is the unprotected answer, and it is not really the interesting question. Let me ask the better one. With equipment, where could you actually stay? This is a different ranking entirely, because the clocks that decide it are the slow ones. Not pressure and temperature, which engineering solves, but radiation, gravity, and how far you are from resupply. At the top, and this genuinely surprises people, is Venus, the cloud layer. 90% of Earth's gravity, which means the bone and muscle problems that plague every other destination, essentially do not arise. Sea level pressure, so a leak is an inconvenience rather than an instant death. A thick atmosphere overhead, providing better radiation shielding than Mars offers. Breathable air as a lifting gas, so the habitat floats without any additional structure, and it is the closest planet to us, with shorter transit times and more frequent launch windows than Mars. The catch is that there is no ground. You could never land, never mine anything, never build with local material. Everything would have to be flown in forever, and you would live your entire life above a surface you could never touch. Second, and for very different reasons, Titan. It is the only place where you could walk outside in a heated coverall. The atmosphere shields you from radiation extremely well. There is abundant material on the surface, and the low gravity that makes flying possible also makes construction and movement easy. The catch is distance. Titan is about 1.5 billion kilometers away. Sunlight there is roughly 1% of what falls on Earth, and any journey is measured in years. It is the friendliest surface and the loneliest address. Third, Callisto, sitting quietly outside Jupiter's radiation belts with water ice and a stable geology, and nothing much happening. Fourth, Mars, which is the compromise candidate, reachable, workable, with a suit that functions like a coat, and with the slow clocks of radiation and low gravity and toxic dust running underneath everything. Fifth, the Moon, which is close enough to be practical and harsh enough to be difficult, and which will almost certainly be first regardless of where it ranks. And that is the whole solar system. Sorted. One place where you were born, 2 places you could visit without a pressure vessel, a handful where you could stay a while with a great deal of help, and everywhere else, 90 seconds. Let me leave you with the thing I actually think about when I do this arithmetic. It is not that space is dangerous. Danger implies something aimed at you. It is that everything out there is simply the ordinary result of physics running for 4.5 billion years on a particular quantity of material at a particular distance from a star, and that almost every outcome of that process is a place where the chemistry you are made of cannot proceed. Venus and Earth are nearly the same size. They formed at nearly the same time out of nearly the same material in nearly the same neighborhood. Something in the details went differently, and one of them ended up with oceans and the other ended up with a surface hot enough to melt lead. Mars had rivers. You can see the deltas from orbit. It was too small to hold its heat, and its magnetic field faded, and its air was stripped away. Over billions of years, and now the water on your tongue would boil there at body temperature. None of these are failures. They are just what happened rock and gas and gravity and time, arranging themselves lawfully with no preference at all about the outcome. And in one place, out of everywhere we can see, the arrangement came out such that liquid water sits on a surface at a pressure and temperature where carbon chemistry can get complicated. And it stayed that way, more or less, for long enough for the chemistry to become extremely complicated indeed, and eventually to sit up and start counting the other planets. And it is worth being precise about how narrow that came out to be, because it was not simply a matter of being the right distance from the sun. Distance matters, certainly. There is a band around a star where liquid water can be stable on a surface, and Earth is in it. But Venus is arguably at the inner edge of that band, and Mars is arguably within the outer edge, and neither of them has an ocean. The distance was necessary, and it was nothing like sufficient. Several other things had to go right, and none of them were guaranteed. Earth is large enough to hold its internal heat. Mars was not, and its core cooled, and its magnetic field faded, and its atmosphere was stripped away. Size is destiny for a planet, and Earth came out on the correct side of a line that Mars missed. Earth has plate tectonics, which, as far as we know, no other body in the solar system currently has. That matters more than it sounds, because tectonics drives a slow carbon cycle. Carbon dioxide dissolves in rain, weathers rock, ends up in ocean sediment, is carried down at subduction zones, and is returned to the atmosphere by volcanoes. That loop acts as a thermostat over geological time. When the planet cools, weathering slows, carbon dioxide accumulates, and the greenhouse effect strengthens. Venus, without that loop, went the other way and never came back. Earth has a large moon, and it is unusually large relative to its planet, almost certainly the result of a collision very early on with a body around the size of Mars. That moon stabilizes the tilt of Earth's axis, holding it within a narrow range over millions of years. Mars, with only 2 tiny captured rocks, wobbles considerably. Its axial tilt has varied over a wide range, producing climate swings far more extreme than anything here. And Earth has a liquid iron core still churning after 4.5 billion years, generating the field that turns aside the particles arriving from the sun and the wider galaxy. Any one of those going differently, and the room you are lying in would not have air in it. None of this means Earth is unique in the universe. There are a great many stars and a great many planets, and the current best estimates suggest that rocky worlds in the habitable zones of their stars are common rather than rare. The point is not that this arrangement is impossible elsewhere. The point is that within reach, within the entire system we can actually go to, across every world we have ever photographed or landed on or flown past, it happened exactly once. Take a slow breath now if you are still awake at all. Notice for a second that you can. There is a column of air above you, and it is pressing on you at exactly the right amount to keep your blood liquid, and it is about a fifth oxygen, which is exactly what your cells need. And its temperature is somewhere your enzymes can work, and above it there is a magnetic field turning aside particles from the far side of the galaxy. 4 things, all of them free, all of them holding steady tonight, as they have every night of your life, without you ever once having to check. Out there right now, Venus is 462 degrees in the dark and in the daylight, all the way around. Jupiter is falling into itself forever, with no floor anywhere in it. Uranus is lying on its side in the deepest cold in the solar system, halfway through a 42-year night. Triton is throwing nitrogen 8 kilometers into a sky that is almost nothing at all. And somewhere out beyond Saturn, on a small orange world, under a haze of hydrocarbons, waves of liquid methane are moving very slowly against a shoreline made of ice, in a place where a person could fly and where nobody has ever been. None of it needs you. None of it is waiting. You are in the one room with air in it. The window is closed. The blanket is where you left it. The pressure is holding. Sleep well.